on life. I inserted one here, right? Waiting for students, and I have become waiter. Bro, today also my phone is out of order. I have ordered a new phone. I don't know when it would be reaching here. So till I get my new phone, you should help me. You could help me. Cool. Oh my god, I forgot this is being recorded. Where did students go? Hi Rahul, good afternoon. Hello Rahul, ಹೇಗಿದ್ದೀರಾ? Hope everything is going cool at your end. ಹೇಗಿದೆ ಮೈಸೂರು? So waiting for more students to arrive, guys. Hi. So hope everyone are here. Uh, Robinai. Hi, Anusha. Good evening. Good afternoon. So hi guys. Hi. Good afternoon. So everyone, happy Monday again. So we are back at work. Hope everyone is able to hear my voice clearly. I don't know why did this stop. Okay, guys, please take your technical check again. Please take your technical check again. If let me know if my voice is audible and my screen is visible to all. Hi, Anusha. Good afternoon. Good afternoon, everyone. Good afternoon, Prajwal, Priyanka, Rahul. So, yep. So, in today's class, we'll be discussing about the continuous charge distribution and also about the electric flux. Okay. So, we'll be starting with a new concept that is the electric flux today in today's class. Good afternoon, guys. So, hi, YouTubers. Good afternoon. Hope everyone are here. So everyone try to revise your concept so far and have tried to learn the things which were taught in the earlier classes. So guys, I want every one of you to try to be active as much as possible and try to answer all the questions which I ask. Okay. So today's session would be mostly of kind of theoretical. So most of the concepts would be like a derivation of expression and also about knowing something new. Okay. So, yes. So I want every one of you to take and pay lots of attention today and help me take the class. Okay, guys. So I'm going to end the poll now. Hope everyone is audible and visible. Cool, guys. So, guys, please give me the steps. So, in our previous class, we had studied about the electric field and electric potential due to what? In our previous class, we had studied about electric field and electric potential due to dipoles, right? We studied about dipoles. So what's the electric field due to dipole, guys? What is the electric field due to dipole? Electric field due to dipole. Okay. So we had studied about electric field due to dipole. So there were two conditions, one on the axis and on the equatorial plane. On the axis, the electric field was given as E is equals to, guys, if you remember, E is equals to, it's 2 times of P divided by 4 pi epsilon naught r cube. Okay. So this was the expression for electric field due to dipole on the axis, on the axial point. Or this is with neglecting A. If we don't neglect A, then what would we get? If we don't neglect A, the expressions, guys, this is just a revision of what we had learned in our earlier classes. That is Q by 4 pi epsilon naught times of 4ar by r square minus a square whole power 2. This was in the p cap direction. This was for the electric field due to dipole on the axis. Okay. Next thing was, yes, we studied about electric field on the equatorial point. Yeah, what was that? On the equatorial point, it was E is equals to, I'll write the general expression, E is equals to 1 by 4 pi epsilon naught into 2aq by r square plus a square whole power 3 by 2. So this was the expression which we saw for the electric field at a point without neglecting a. With neglecting a, this a would cancel. I'll get r cube again in the denominator. That's the only difference, right? So next we learned about electric dipole in an electric field. Dipole in electric field. What happens when we keep a dipole in electric field, guys? Reply. When we keep an electric dipole in the uniform electric field, what happens? What happens when you keep an electric dipole in the electric field, uniform electric field? Reply. So I have a dipole which is kept in the uniform electric field. Avada? Yes, they experience a torque. So when this is kept inside an uniform electric field, the dipole experiences a torque. Dipole experiences torque. Okay. The dipole experiences torque. Is it always dipole experiences torque? Correct. But is it always? Does the dipole exhibit or experience torque always? No. It depends on situation. It depends on what then? It depends on three factors, or one factor actually here. It depends on theta, the angle between the dipole orientation or dipole moment and the electric field. It depends on the angle between the dipole moment and the electric field, right? If my dipole moment angle is 0 degree, what is the force or what is the torque? Guys, reply please. If my Okay, thank you bro. If my angle between the dipole moment and electric field is 0 degree, then the torque experienced is, yes, correct, Ramakrishna will be correct. Yes, correct, Priyanka. Yes, yes, it experiences a torque, right? So if I keep the dipole in an angle 0 degree with respect to the dipole moment and electric field, what is the net dipole moment, or what is the torque experienced? Torque experienced is, guys, everyone, Tejas, Amrita, sorry, Amrit, error is really. So Prajwal, Amrit, Rahul, Tejas, guys, try to answer this. ನೋಡಿ ಗೊತ್ತಿರುತ್ತಲ್ವಾ, ಆನ್ಸರ್ ಮಾಡಿ. Arun, Anusha. So what's the answer? Yes, that torque, correct, Priyanka, correct, Ramakrishna, correct, Bhargav, correct, Prajwal. So the torque experienced will be 0 in this case, right? Suppose the angle between them is theta is equals to 90 degree, then torque experienced is, if theta is 90 degree, then torque experienced is maximum, right? Yes. Excuse me. Then the electric field between, okay, then the electric field experienced by the dipole, we know that. Then what? Okay, then we also learned about potential. What was the expression for potential due to dipole? Guys, we learned about the potential due to dipole. What was that? So V dipole, potential of dipole is given by one common expression, guys. At any point is given by minus P cos theta by 4 pi epsilon naught r square. Correct. Okay, this was the potential experienced by dipole. That is V dipole is equals to minus P cos theta by 4 pi epsilon naught r square. So if we want to find for axis, what should I substitute theta as? If I want to find the dipole moment along the axis, what should I substitute my theta as? Axis ಅಲ್ಲಿ find ಮಾಡಬೇಕಂದ್ರೆ dipole potential theta na ಏನಂತ substitute ಮಾಡಬೇಕು? What should I substitute my theta as when my potential should when I should measure the potential along the axis? Yes, 0 degree. Then what would I get? Potential V axis will be minus P by 4 pi epsilon naught r square. And on equatorial plane, theta is equals to 90 degree. My potential is 0. Right. So we also learned about external work done, or the external torque applied. So W external was given by, okay, I'll write the expression P cos theta 1 minus P cos theta 2. So this was what we had learned so far. So in today's class, we'll be learning about continuous charge distribution. Okay. So what do you mean by continuous charge distribution? Okay, guys. So I hope everyone remembers this much. Hope everyone remembers this much of what we have learned in our previous classes. Hope everyone remembers about this. Yes, please reply. Reply madbeku. Yep. Okay, guys, cool. So in today's class, we'll be studying about the continuous charge distribution. Okay, what is continuous charge distribution? Tell me, What do you mean by continuous charge distribution? Say, you know, what are the three different types of mode of charge transfer which we studied in a very early class? In our very early class, we had studied about modes of charge transfer, right? What are the three different types of modes of charge transfer? Yes, one was conduction, correct. So the three different modes of charge transfer. One is conduction. Next, two, yes, induction. Three, friction. Yes. So these were the three modes of charge transfer. Now, guys, among these three modes of charge transfer, which of the modes of charge transfer gave the same type of charge? Which of these had the same type of charge? Conduction, induction, or friction? Anusha, are you right? Prakash, correct? Is it right? Yes, Prajwal, correct. So guys, in case of friction, see, in case of friction, if you have forgotten, so we had a sweater, woolen sweater, if you remember. Yes, I'll try to draw that. We had an woolen sweater. So this sweater was neutral. I got a balloon. So we try to rub this woolen sweater. So the woolen sweater got a positive charge, net positive charge on its body. The balloon got negative charge. So this was the conduction by friction, right? So we'll use the general formula, Bhargav. So the general formula for finding the potential is V is equals to P cos theta by 4 pi epsilon naught square into R square. So this is the general formula which we use, Bhargav. So if theta is equal to 0 degree, say along the axis, my theta will be equals to 0 degree, right? Along the equatorial plane, my theta will be exactly 90 degree perpendicular. So substitute the value you'll get. So along the perpendicular direction, my electric potential will be zero. Okay, guys, coming back. So in friction, there were the process of two different charges, right? So even in the case of conduction, when I got this negatively charged balloon near the wall, what happened? When this charge balloon was brought near my wall, which was neutral, it pushed away all the negative charges away, and there was a net positive charge created. Even here, there were two different types of charges formed. But in case of conduction, what happened? In case of conduction, what happened? So the conduction, there were two conditions. So there, when I bought a charged body, say if a charged body is continuously charged with positive charges, when I bought an uncharged body near it, and when I touched this, so what happens? So all the positive charges from this charge body was flowing here, right? So only in conduction, same type of charges is being transferred. Only in conduction, guys. Please remember that only in conduction, same type of charge transfer is occurring. So when this, okay, let's assume such type of charge transfer is occurring. Now, the charge can be distributed uniformly in three ways. Okay, that is, say if we are uh, trying to conduct, or if we are trying to charge a linear body, if we are going to try to charge a linear body, then we will call that charge distribution as linear charge distribution. Suppose if we have a surface area and we want to provide charge to that surface area, then when we provide the charge and the charges go stick to the surface of that body, then the charge distribution is called as surface charge distribution. Then one more, we have volume charge distribution. Say suppose we have a volume of an object. Now when we try to give charge to that body, the all the charges are accumulated on the volume of that body. Then such charge distribution is called volume charge distribution. Okay, so sir, this is very confusing. What is surface charge? What is volume charge? What is linear charge? Let's check that with an image. Okay, so let's learn about linear charge distribution. So to learn about linear charge distribution, let us consider a conductor. Okay, let this be a conductor of length L. Let this be a conductor of length L. Now assume I have a charged body. I have a charged body which is positively charged. Okay, I have a charged body which is positively charged. Now what happens when I touch this? What happens when I touch this? Guys, what happens when I touch this conductor? So this is a conductor. This is a conductor. Okay. So this is a metal conductor. This is another charged body. When I touch this conductor by this charged body, what should happen? Reply, guys. Gotilva. Yes. So half of its charge would be transferred here. Say some amount of charge is being transferred to this. So okay, say okay, some amount of charges transferred to this. Now all these charges, when they are being transferred, they accumulate throughout the surface evenly, uniformly. Okay, when I apply this charge, when I give charge to this conductor, now what happens? All the charges accumulate on this conductor uniformly. Okay, this is very important. It's uniform. Okay, then if I call Q as the total surface charge on this conductor, so if I call Q as a total surface charge, or say on this conductor, the Q amount of charges get accumulated on its throughout its body. Then this type of charge distribution is called as linear charge distribution. This kind of charge distribution throughout the conductor in a linear conductor whose area is negligible. Cross-sectional area is the alarm. When the cross-sectional area is there now, its area is very, very thin. It's negligible. Such charge distribution where my length is L, which is very, very, very large, in which my charge distribution takes place, such type of charge distribution is called linear charge distribution. Okay. Now, the linear charge density. What is density, guys? What is density? Yes, yes, exactly, Karthik. Exactly like that. So what is density, guys? Density formula. Yes, it is mass by volume, right? Suppose if I ask you what is, okay, this is the general form of density where we consider the any volumetric system. Suppose if I have a linear system, then say if I want to in this, yeah, this is mass by volume, yeah, density, normal density, we know it's mass by volume. Suppose if you want to find the charge density, how is it given? So the charge density, the linear charge density, please make a note that just the linear charge density, the linear charge density will be given as lambda. Guys, remember this. If you have a notebook in front of you, make a note of this, try to practice this, this is very important. The linear charge density is given by lambda, and that is given as charge by length, the total length of this. So symbolically, if I want to write this, I can write as lambda is equals to Q by L. Okay, where Q means the charge and L means the length. Okay, so what can be its unit, guys? What can be its unit? What can be its unit? Haley, the linear charge density, it's coulomb per meter. Okay. Yes, cool. So this is my linear charge density. So guys, if you remember, so similarly, we will solve for a ring. Okay. So consider a ring. So consider a ring of radius r. Say if I have a ring of radius r. Now, if I give the same amount of charge to the ring, what happens? All the charges will be accumulated. Okay, I missed one charge here. Okay, all the charges would be accumulated. Say if Q amount of charges accumulated on this ring. Now, how to solve? How to solve such problems? Say, I think you try to find the electric field of such product, I mean, such object in your DPP1. Guys, I hope everyone try to solve this. In your DPP1, there was one question, I think question number 2, which was a ring, right? So we'll learn today how to solve the problems of such extended objects whose electric field will derive an expression for electric field of such object. Okay, today. Cool. So if we have a ring, how to solve this, guys? Any idea how to solve? Say if we have a ring like this, I want to find its charge density. How can I do that? ಹೆಂಗ್ ಮಾಡೋದು ಹೇಳಿ? So what I'll do, I'll take a scissor. Okay. Yes, cool. So what I'll do, I'll take a scissor. Okay, I don't know if I am. So I'll take this scissor. Okay, I'll cut this. I'll cut this ring into touch. I cut that. Then what happens? I'll expand this ring. So what will I get if I cut this and expand this ring? I'll get a linear conductor, right? I'll get a linear conductor. Correct, Karthik? Super. So I'll get a linear conductor with the same amount of charge. But what is the length of this linear conductor? This linear conductor will be having the length of circumference of this ring, right? Will be having a length will be equals to circumference of this ring. So my L will be equals to 2 pi r. Correct? Then my linear charge density will be given as lambda is equals to charge by length, that is lambda is equals to q by 2 pi r. So this is the expression which we are going to use to calculate the linear charge density of any ring. Okay, got this, guys? Yes, this is easy for you now. Okay, come on, let's check for others. So what happens for the surface charge density? So to know about the surface charge density, let us consider a sphere. Okay, to know about the surface charge density, let us consider about the sphere of radius r. Okay, let us consider a sphere of radius r, and let q be the charge on the sphere. Let q be the charge on the surface of the sphere. Then the surface charge density. What is surface charge density, guys? The surface charge density is given by small letter Greek alphabet sigma. Okay, this is called as sigma, the Greek alphabet. So the surface charge density is given by sigma. So sigma will be equals to charge by surface area or charge by area in general. What is the area of this sphere? So what is the area of the sphere? It is 4 times of pi r square. 4 times of pi r square, right? Then the surface charge density all over the sphere. So what happens, say, assume, if you want to know about the sphere, assume you have a ball and you apply some paint on the ball, or you pour some charges on the ball. What happens? All the charges, or say it's like apply some fevicol on the ball and try to put sparkles on the ball, glitters, you know na, glitters. You try to sprinkle the glitters. What happens? All the glitters will accumulate on all the directions of the ball, right? In all the surface, entire surface area, my glitters will come and um, stick onto that ball. So it's similar to that. Even my charges, when we supply the charges, the entire amount of charges will be on the surface of the sphere. So it will be more like coating, like it will be more like a charge surface. On the outer surface of the sphere, there will be charge accumulated. So this is given by sigma, the surface charge density, that is charged by total surface area, that is 4 pi r square. Okay, guys, got this? So please remember all the formulas. These are very, very important. Next, we have a special case. Okay, the surface charge density. So we learned about the sphere. Similarly, we have a surface. I mean, a plane surface. A plane surface. So how many ends does a plane surface have, or how many faces? How many faces does a plane surface have? Yes, we have two surface, right? One is, say, this is one surface, and on the other opposite side, say on the opposite side, if I want to turn that opposite side, I have to come to normal view. Then I can try to turn this. So this is one surface. Then if I want to turn this to the other surface, I can turn like this. So this is my one. Okay, if I call this, yep, I can turn like this or I can turn like that. So if I call this one as one, this other opposite side should be two. Okay. So I have two surfaces. For plane, I have two surfaces. Hope everyone knows this. I'll tint it to the initial direction. Okay. So, yeah, since it has two surfaces, what happens in the case of my planar surface? So this is first surface one, and the other end has surface two. Then the linear charge density, the surface charge density, then the surface charge density for the sphere or the side one. The surface charge density for side one will be represented in this way. So you could see here, this is side one, the other end is side two. Then the electric field lines passing on the other side. Okay, I will use a different color for this. Then the electric field passing through this surface. Say if I apply some charge Q1, say if I apply some charge Q1 here, I'll get, okay, this should be charge Q2. Yes. Yes, if we supply same amount of charges, if we supply Q1 amount of charge here also and Q1 amount of charge there also on the other end also, both will have the same magnitude, both can have the same magnitude, but the electric field direction will be opposing. So one for this electric field, I mean for this surface, the electric field will be normal to this surface. Okay, for this surface, the electric field will be normal to the second surface. So if this is my first surface and this is my second surface, the electric fields emerging out of these, it need not be, it can be. Yes, Hari Prasad, it can be or it need not be. Say if I supply Q1 amount of charge to this, and if I give Q2 amount of charge to the other surface. Okay, so there can be two different charge surfaces, or if I supply the same amount of charges also, if I supply same amount of charge Q and Q, then both will have the same amount of electric field. Alva, sorry, right? Then the electric flux, the electric field or the electric surface charge density sigma will be given as Q1 by A1 for first surface. Similarly, the surface charge density for Q2 sigma 2 will be given as Q2 by A, whereas A is the area. It need not be only positive, it can be negative also. So it need not be always positive, it can be negative also. So the surface charge density can given as charge by area sigma is equals to Q by A. Okay, guys, one more thing. Say if I want to find the net surface charge density, if I want to find net surface charge density, say I have one special case, guys. This we will be studying again in our parallel plate capacitor. I hope everyone have completed parallel plate capacitor in your school. Yes. Suppose if I have a parallel plate, I mean, if I have a plate like this, it's a planar surface, right? Hope everyone have completed parallel plate capacitor. Yes, no, something, please reply. Yes. So what happens when we are deriving an expression for parallel plate capacitor in this case? Say in parallel plate capacitor, we only give Q. We only supply a charge of magnitude Q to this plate. Okay. What happens? One end of the plate will have how much charge would be distributed in this case, guys? If I have Q amount of charge, okay, I'll give you a number. If I have 10 charges, 10 Q charges, now how will you distribute on this planar surface? Guys, if I give you 10 amount of charges and ask you to distribute uniformly, how will you distribute? So how many charges would be on first phase? How many charges would be on second phase? Yes, correct, Karthik. Others, guys, try to answer, please. Say how many faces? Yes, correct, Karthik. Others, please try to answer. So I have 10 charges. I give you those 10 charges and I give you this plane surface. Now I ask you to distribute these charges uniformly. How will you distribute? So only one person, only one student had given me the right answer. Others, guys. Mm, yes, correct. Correct, guys. Priyanka, correct. Aghosh, correct. Madhavi, correct. Others, guys, JPMC students, please try to answer. Navodaya students, try to answer, please. ಕರ್ನಾಟಕದವ್ರೆ ಆನ್ಸರ್ ಮಾಡ್ರಿ. ಯಾಕೆಲ್ಲ ಇಷ್ಟು ಸೈಲೆಂಟ್ ಆಗೋದ್ರಿ? ಎಸ್ ಕರೆಕ್ಟ್ ಭಾರ್ಗವ್, ಕರೆಕ್ಟ್ ಹರಿಪ್ರಸಾದ್. So guys, yes, ಏನಾಗುತ್ತೆ? So what would happen here in this case? I will be having 5 charges on one face, another 5 charges on the other face. So what happens to the electric charge density on first phase? What is sigma 1 here in this case, guys? What could be sigma 1 in this case? How can I write sigma 1 in this case? Sigma 1 equals to how much? Half of q, right? Q by 2 times of a. Similarly, yes, 5. Say I want a general expression, guys. Please try to answer with general expression. It is q by 2 times of a, right? Q by 2 into 1 by a. Similarly, sigma 2 will be also q by 2a. So when I'm trying to give some amount of charge and I'll try to distribute equally, then I'll be having sigma is equals to q by 2 times of a amount of charge density on one of the sides or one of the faces of my planar surface. Okay, this I think most of you had experienced, or most of you might have confusion how we got this sigma value as q by 2a in our capacitors. Did anyone have this doubt? Yes, it may be different, it may not be different. In this case, I gave q as same. Yes, actually in case of capacitor, it will be different, Karthik. Okay, guys. Yes, cool. Yes, please try to answer with the general expression. It's q by 2 into 1 by a. Okay. Okay, guys, come on. So I hope by this you know, or you might have understood what is planar surface or surface charge density due to planar surface. Next, we'll learn about volume charge distribution. So what is happening in this case? Say I have a shell. Hope all of you know how a shell looks like. How many of you know? How many of you have broken coconut shell? How many of you have broken coconut? Boys, girls, yes. Yeah, only one. One so far. Only one. Okay, cool. Rajwal, Sai, Teja, everyone. Yes, everyone have done this, right? So, how would it look? Or how many of you have cut this cricket ball plastic? I mean, we used to get this 8 rupees cricket ball in our childhood, no? So in our childhood, while playing cricket, we had this some plastic type of ball like this. It had some dash structure like this. So this was some 8 rupees ball. Pepsi ball. Yes, exactly. Yeah, hollow inside. So how many of you had cut this ball? How many of you had cut this ball? Yeah. So if you have cut this ball or if you have broken a coconut, how does that look like? How does that look like? So it look something similar to this. See, it will be having something like this, right? Yep. So now suppose assume I have a surface like this. So this is nothing but a shell. Okay. Yes, this is an hemisphere or a shell. This is more like a hemisphere. Say any surface which is similar to that of hemisphere or which has a hollow space, this can be considered as a shell. Okay. So this is the front view. From front side we can see like this. From side we can see like this, side view. Okay. Side in the node ring kansate, front in the node ring kansate. Suppose, yeah, if I have an inner radius of r2 and an outer radius of r1. Okay, I have an inner radius of r2 and outer radius of r1. Then if I try to give, suppose this is a metal ball, metal semisphere. Suppose this is a metal semi hemisphere. Okay. Hemisphere. Then how can I give? How can I give my electric field? Okay, if I supply some electric field to this, what happens? So when I try to supply some electric charges or electric, yeah, when I try to give some electric charges, what happens? Correct, Karthik. So these charges accumulate inside this surface. Then these charges are accumulated on the volume of the shell. Then the volume charge density will be given as rho. Okay, for volume charge density we have the symbol as rho, that is charge by volume. Okay, so the charge the volume charge, I mean the volume charge density is given by charge by volume. So what is the volume of this hemisphere, guys, or volume of the shell? Okay, based on the volume of the shell we can find. Okay, if we know the volume of the shell is 4 by 3 pi times of r cube, volume of shell is 4 by 3 pi r cube. Okay, if you know that, then we could find in which region is my charge distributed. Only in the mid region, right? Between r1 and r2. See, if you see, between my r1 and r2 only, between the r1 and r2 only I have my charge being distributed. So I will write my charge distribution as q by 4 by 3 pi r1 cube minus r2 cube, the difference between these two. R1 is the higher radius, the bigger radius, R2 is the smaller radius. So the change in or the charge, the volumetric charge distribution or volume charge density is given by charge by change in volume. Okay, guys. So what was again? Come on, tell me. What was the linear charge distribution given by? Linear charge distribution was given by. Yes, what was linear charge? Lambda. Lambda is equals to Q by L. Correct, Karthik. So surface charge distribution was given by lambda, sigma, or pi, psi, omicron, whatever. It was given by sigma. Sigma is equals to Q by surface charge area A. And similarly, my volume charge will be given by rho, that is Q by A. So this is linear, surface, and volume. Okay, so linear, surface, and volume charge densities. Okay, these are the three things which you have to remember. Okay, okay, guys, done, understood. So this is the general basic which we require. Now we'll study about the electric field. Electric field due to continuous charge distribution. Okay. Oh, right. This is Q by V. Cool. Thank you. Thank you. So in all three cases, it is okay. What are the SI units? If they ask you SI unit, it's coulomb per meter for linear, then coulomb per meter square for area or surface area, then for volume it is coulomb per meter cube. Okay, cool, Anusha, cool, thank you, awesome. So next we'll be studying about the electric field due to continuous charge distribution. So we'll be studying about infinitely charged conductor. So I have an infinitely charged conductor. Now, how to find its electric field at a point R? So I have a point R here. So at this point R, how can I find the electric field? So can I find the electric field throughout this conductor by all means at all points? Yes, no. Can I find the electric field due to this conductor at all points? Yes, I can. If I have so much of time, I can, but I don't want to. So what I'll do, I'll consider. So let us consider a infinitely long current carrying conductor, and let us consider a small particle dl. Okay. let us consider a small, yeah, elementary portion dl, and let us consider a point r where we have to find the electric field. Now what happens, guys? At this point r, the elementary charge, the elementary charge particle, sorry, elementary portion of this length dl. So I have the infinitely charged conductor. Out of this, I'll consider a small conductor of length dl. Now this length dl makes an angle d theta. See, this length dl makes an angle d theta with the point r at a length l. So this length l from the origin, say if I consider this as my origin or the horizontal, from origin at a length l, I have an angle. This small angle, a small elementary portion dl makes an angle theta with the horizontal, and this small portion makes an angle d theta with the point r. Similarly, now, what happens? The electric field will be along this direction. See, if you see, the electric field will be along this direction. Electric field will be along this direction, DE, right? The electric field will be along this direction. What happens now? If can I find the magnitude of this electric field DE due to this small particle easily? Can I directly find the value of DE or the magnitude of DE because of this small particle dl at this point r? No, right? To simplify that, what we do, we'll try to we'll try to split we'll try to split the electric field into two, one along horizontal direction, one along vertical direction. Yes, we try to split or resolve. Yes, we'll resolve this electric field DE to x-axis particle horizontal components and vertical components. Now what happens? The horizontal component is given by dex, that is d cos theta. So if this makes an angle theta here, this also makes an angle theta here, right? Now this gives me dex, that is, this is dex is equals to d cos theta. Similarly, my dey will be de sine theta. Now what happens, guys? If you see, if I consider another element dl, and making an angle d theta again with the horizontal with an angle theta as a length l at the same distance of length l. Now what happens, guys? At this point, what happens? There will exist yet another electric field dE in this direction, right? There will exist another element or electric field dE in this direction. Now, if I try to resolve this also, I'll get a dex along this horizontal component. Now, what happens to the vertical components, guys? If you see, yes, my vertical components gets cancelled. Okay, my vertical components get cancelled. Then my horizontal components get added up. Right now, okay, one more geometrical configuration, one more geometrical simplification I have to do. I have to calculate the value of x. Okay, I want to calculate the value of x. How can I calculate the value of x, guys? Say they have given the separation between this origin or the horizontal point or the point O from this infinitely charged current carrying conductor, have this point r at a distance of small r. Okay, have this capital R at a distance of small r. Now, if this is r and this is l, then what should be my x? What should be the value of, what should be the length of or the magnitude of the distance between the point r and the point of my small portion dl? So to find x, what should we do? We have to consider cos theta. So to find x, we have to consider cos theta. So what we take cos theta as adjacent by hypotenuse. From here, can I find the value of x? Yes. Can I find the value of x? Say I know r, I know x. Can I find the value of x using cos theta? Yes. We know that cos theta is equals to r by x, or x is equals to r cos theta. Sorry, r by cos theta. X is equals to r by cos theta. From here, what is 1 by cos theta, guys? 1 by cos theta was nothing but sec theta, right? Yes, correct, Tejas. So I'll substitute that value here, and I'll get x is equals to r sec theta or secant theta, right? Now we'll use all these three. So what should we find? We have to find dex. What is the value of dex due to both of these components? Yes, correct, guys. Next, we'll try to find the value of dex. So dex will be equals to, yes, excuse me, dex will be equals to de cos theta. Now, if we try to simplify, or if you know, what is the expression for electric field, guys? We had studied earlier, right? Electric field between 2 points or 2 point charges. Yes, F by Q. That is, yeah, E is equals to F by Q. That is K times of Q by R square, right? So if I try to simplify this, that is electric field E is equals to Q by, for this case, if I am applying electric field, I'll get Q by, okay, 4 pi epsilon naught x square. Now guys, since this is a linearly charged conductor, what is the linear charge on this? Since this is a linearly charged conductor, what is the linear charge density given by? Yes, lambda is given by Q by L, right? Correct, Tejas. Correct, Karthik. Others, guys, please try to respond. Come on, guys, please try to respond. So my linear charge density lambda is equals to Q by L. From here, how can I write my Q? Yes, how can I write my Q from here? How can I write my Q here? From here, I know lambda is equals to Q by L. This is the only data I know about it. So how can I write Q value? Q is equals to, so cross multiply, guys. What will I get? Q is equals to lambda times L, right? I'll get Q is equals to lambda times L. Correct, Karthik. So, okay, now help me write the expression for DEX. What is DEX? What will be my DEX? Help me write it. So DEX will be equals to, guys, since I have a charge DE, so I know only Q, right? I know only Q. Have considered a small element DL, so I can write Q as Q is equals to lambda times DL. So can I write this? My Q is equals to lambda times DL. At this small element DL also, there will be a charge Q. There will be a uniform charge Q throughout this length. So at this DL also, I'll be having same amount of charge Q, or there will be equal magnitude of charge Q, right? Yes. Then how can I write my DEX? DEX is equals to, so I'll try to write this in general form now. DEX is equals to dq cos theta by 4 pi epsilon naught r secant square. Okay, for now. Next, I'll replace this dq. So I know in continuous charge distribution, lambda is equals to q by L, then q is equals to lambda times L. Then since I have a small n dl, then q is equals to lambda dl, right? This we had studied just now. Then how can I write my expression dex? Dx can be written as lambda times dl cos theta by 4 pi epsilon naught r square secant square theta. This is my value of x square. Guys, if you remember, this is my value of x square, and this is my value of q. So I have replaced the value of q and x square here. Any doubts so far, guys? Any doubts in this derivation? Any doubts in this derivation? Please reply. No. Okay, cool. Next, I have to find what is the value of dl. How can I do it? Okay, so some Yes, Karthik, please let me know if you have any doubts. Okay, so I had this, but now guys I have. Okay, is anyone copying, guys? I'll be sharing these notes. Okay, if anyone is copying, let me know. If anyone is writing, please write along with me. Yeah, you can also take screenshots. But anyway, I'll be sharing you the notes. Okay, I'll be sharing this entire PPT with you guys after the end of this class. You can also take the notes. Cool. Okay, now I have one question. How can I find my value of DL? What is my DL, guys? DLA, no. How can I find my length DL? So do I know anything about L here? Yes, it's a part of L. Do I know anything about L here? L. Yes, we can try to do that. Yes. If I do I know anything about L and R? Can I use L and R somewhere here? What happens if I want to find my theta or L and R? So guys, so by this formula, we know that L by R will be equals to tan theta. Okay, from the above equation, from the above image, you know that L by R will be equals to tan theta. From here, how can I write L as? Yes, to find L or to find DL, I can write my L as R tan theta. Now, if I try to differentiate this, I'll get DL is equals to R secant square theta d theta. Okay, I hope everyone knows this. Differentiation of tan theta is secant square theta, and applying chain rule, my theta will be differentiated, so I'll get d theta. My theta will be differentiated with respect to DL, so I'll get d theta. Yes. So DL will be equals to R secant square theta d theta. So if I try to differentiate this, what I'll get? DL by, okay, L by DL or DL by DL is equals to R tan theta into d theta by DL. So then DL will be equals to R secant square theta d theta. If you try to differentiate tan theta, you'll get secant square theta. Hope this is known by everyone. Yes. Any doubts in this, guys? Any doubts in this? Cool. So if we try to substitute everything, what we get? We'll get lambda r secant square theta d theta cos theta by 4 pi epsilon naught r square secant square. From here, I can cancel my r and r, secant square theta and secant square theta. Okay. I'll cancel my r in numerator, denominator, and secant square theta in numerator and denominator. So I'll get my dex. What will I get dx as? Dex will be equals to lambda times cos theta d theta by 4 pi epsilon naught r, right? This will be the value of dex. Next, so on simplifying, we'll get lambda times cos theta d theta by 4 pi epsilon naught r. Now we have to integrate to get the value of E, right? So to get the value of total electric field throughout, yes, integrating both sides, we get, so dx is equals to integral minus pi by 2 to plus pi by 2. Why minus pi by 2 and plus pi by 2, guys? So if you remember, my electric field for this infinite long wire, say this infinite long wire at this point R. So what is the angle made by this point R with this infinitely long wire? At this case, it is plus pi by 2. And for the other end, it is minus pi by 2, right? Yes. Cross multiplying, yes, we did the same thing, Hariprasad. We try to find that by cross multiplying only. Okay, now we know the angle between the 2 points, I mean between the length and the point R as plus pi by 2 and minus pi by 2. Applying that, we get, okay, integration of cos theta. Yes, sine theta. Then by substituting the values, we get, yes, what do we get? Ex will be equals to lambda by 4 pi epsilon naught r into sine 90 sine pi by 2, yes, minus of sine minus pi by 2. What will I get, guys? So this will be equals to lambda by 4 pi epsilon naught r into sine 90 is 1 minus of minus 1. So I'll get lambda by 4 pi epsilon naught r into plus 2. So this 2 and this 4 cancels. Then we get Ex is equals to lambda by 2 pi epsilon naught r newtons per coulomb or volts per meter. This is the expression for electric field due to continuous charge distribution. Guys, now everyone, you can use this formula for calculating the electric field due to the infinitely long charge current carrying conductor. Also, you can use the same formula to calculate the expression for or the electric field due to the ring also. Okay. Yes. Okay. Cool, guys. Hope you have understood the electric field expression. Guys, please reply with yes if you have understood the electric field expression. Yes. We'll quickly go to the potential expression. Okay. Okay. Yeah, even that I think Karthik. No, it would be 2 times of dx. Then on simplification, we'll get that. Okay, we'll check that. Cool. Next, the potential due to continuous charge distribution. Okay, let's find the potential, electric potential due to continuous charge distribution. Okay. Yes. Okay. Yeah. Here it should be 2 lambda, right? Okay. Thanks Karthik and thanks Hari Prasad for notifying this. So since we were adding the dx 2 times, it will be 2 times of lambda, but we'll check that. Okay. So you have to take 2 times of lambda again. From there also you get 2 gets cancelled. Yes. When you're trying to find the electric field at that point, but we'll check that. Okay. So we'll try to find the electric potential due to continuous charge distribution next, guys. So what we know that electric field. So for now, we'll take lambda is equals to E is equals to lambda by 2 pi epsilon naught r. Then the electric potential, we know the relation between electric field and electric potential E and V as E dot dr is equals to minus dV. I hope everyone knows this. The electric field due to infinitely long conductor is given by lambda by 2 pi epsilon naught r. Then the relation between E and V will be given as E dot dr is equals to minus dV. So Hari Prasad and Karthik, so it's not only because of 2 lambda, right? Sorry, we won't get 2 lambda there. It's because of entire conductor. See, not only 2 points, we are considering entire point. When we are integrating, so Hari Prasad and Karthik, when we are integrating, we are trying to find the electric field of entire length, not only 2 points, it's entire length, right? So we won't get an extra 2 here. Sorry for that. We won't get an extra 2 here. So when we are integrating only, we are adding all the points, electric field of all the points, right? Alva, Karthik and Hari Prasad, please note that. So when we are integrating only, we are adding all the points. So we don't need to add only those 2 points. Okay. Okay. So no, we don't get a 2 in numerator. No. Okay, guys, next we'll try to find the relation. Okay, we know that the relation between electric field and potential is given by E dot dr is equals to minus dV. From here, if we try to find applying a relationship for infinitely long conductor, we get the change in potential. dV is nothing but the change in potential. So what is change in potential, guys? See, the change in potential simply means, say if I have a charge q here at point B, if I have a charge q here at point B, if I try to move this charge q from point B to point A, I should do some work, right? I should do some work. This work would be stored in this charge as potential energy, and this potential energy per unit charge is called as potential. So when this charge q, small charge q, moves from point B to A, it gains some potential. Say at this point, it will be having a potential of VB. When the same charge goes to this point A, it will have a charge of VA, or potential of VA. Then the net potential gained by the charge will be VA minus VB, right? Initial point, final point. My change in potential will be final minus initial. V final minus V initial. So my V final is VA, initial point was VB. So change in potential is VA minus VB. Since I have to take E dot dr is equals to minus dV, I'll consider this, writing this expression. dV will be minus of VA minus VB, and dr is E dot dr only. So if you want to find the net potential, so this is dVA minus dVB. If you wanted to find the total potential, then what we had to do, we had to integrate on both sides. We get minus of VA minus VB is equal to integral A to B E dot dr. Okay. Any doubts here, guys? Any doubts in any of these? Okay, no doubts. Cool. Thank you. Then the electric potential will be given as, so I have taken the sign, negative sign inside. So what happens? VA minus VB will be VB minus VA, will be integral of A to B lambda 2 pi epsilon naught into 1 by r dr. From here, if I try to take, I'll get my value of lambda by 2 pi epsilon naught as constant. Then integral of 1 by r will become what? Integral of 1 by r is ln r, ln r, from limits a to b. So if I try to substitute, I'll get ln a minus ln b minus ln a. In this case, lambda by 2 pi epsilon naught into ln b minus ln a after this step. So I know log of b minus log of a is log of b minus b by a. Guys, log of b minus log of a is log of b by a. So I'll get this as my expression. So this is my expression for change in potential. That is Vb minus Va is equals to lambda by 2 pi epsilon naught ln b by a. Okay. So this is the expression for my electric potential. Got this, guys? Please reply with us if you have got this. So why should it be upper limit? Okay. So if you consider now what happens, my yeah, I have a doubt, guys. Please listen. So why should we consider the upper limit as A to B only? Say now what happens, I have my charge Q from point B to A. It moved from point B to A. It's at point A now. This is point B. Now what is the net potential, change in potential again? So initially what I did, I moved my charge Q from point B to point A. Howda? Right? Initially I moved from point B to point A. At that point, what was my change in potential? It was, this is my initial point, this is my final point. So V final minus V initial. So ಏನಾಯ್ತು, it was VA minus VB. Right? I had a negative sign also, minus of VA minus VB. Now if I want to eliminate this negative sign was not only for left hand side, it was also for right hand side, right? If I had a negative sign here, and if I had A and B here, so how would it change in my right hand side? So if I had my right hand, in left hand side I had A here and B here, with a negative sign, what would change here? What would happen to the limits, guys, in this case? Reverse. Yes, limits would have been reverse. It would have been motion of my charge from B to A, right? It would be motion of my charge from B to A. Karthik Kelskuli, if I had negative sign and VA minus VB, my potential, change in potential, if it was written like this, then my limits would have been B to A, since I moved my charge from B to A. But here, when I considered the negative point, negative charge, minus charge na ಹಾಕಿದ್ರೆ ಏನಾಗುತ್ತೆ VB minus VA ಬರುತ್ತೆ. So when I substitute, when I put the value of negative or taken in the negative value, so it should change on both sides, right? Then I'll get VB minus VA and integrals will reverse, right? That's what happened. Okay. So any doubts in this, guys, other than this? Again, Karthik, the same, the doubt which you had. So 2 points add agalla. I mean, it's not only the 2 points, we are integrating, right? So all the points will add up and to give us the electric field as lambda by 2 pi epsilon naught. Adu artha agittalva? Please confirm. Hari Prasad? Okay. Okay, guys. So if this is understood, then yeah, its value should be nodes. So please try to answer this question. If that was understood, please try to answer this question. So what we have here, we have an infinitely charged conductor, linear conductor, say infinite line charge, produces an electric field of 9 into 10 power 4 newtons per coulomb at a distance of 2 centimeter. Calculate the linear charge density. They are asking you to find what is lambda. What is linear charge density, lambda? Let's try to solve this. Everyone at YouTube and also at Zoom, please try to solve this. So what is my electric field, guys? Expression for electric field. Any doubts in this expression for electric field? E is equals to lambda by 2 pi epsilon naught r. Any doubts how we got this? So there will not be any 2 here. No, there won't be any 2 in the numerator. Okay. So we are not only adding for 2 points, it's for entire point which we integrated. Now what is the electric field? E is equals to lambda by 2 pi epsilon naught r. Guys, what is the value of this? If you try to solve this, what would we get? Okay, I got one answer. Hope everyone is trying to solve. Please use this formula to solve this. So given electric field is 9 into 10 power 4. Guys, given electric field is 9 into 10 power 4 newtons per coulomb. Electric field is given to us. So also the distance r is given to us. R is given to us and electric field is given to us. Try to find lambda. Check your answer, Manju. So what should I get the expression as? Lambda is equals to E times of 2 pi epsilon naught r, right? Lambda is equals to E times of 2 pi epsilon naught r. So pi lambda is equals to 9 into 10 power 4 into 2 into 3.14 into 8.854 into 10 power minus 12 minus 12. Yes. And what is my r? R is 2 centimeters, 2 into 10 power minus 2. If you try to simplify this, you'll get the answer. So guys, if you want 2 pi epsilon naught, so we know 4 pi epsilon naught is 9 into 10 power 9. What is 2 pi epsilon naught? Okay, only one correct answer so far. So guys, should not take so much time. So 2 pi epsilon naught value is 5.56. 2 pi epsilon naught value is 5.56 into 10 power minus 11. Yes, correct, Devika Rani. Priyanka correct, Ramakrishna Reddy correct, Devika Rani correct. Others, please try to answer. So guys at Zoom, please try to respond. So 2 pi epsilon naught value ಬೇಕಾದ್ರೆ ಕೇಳಿ. It's given as 5.56 into 10 power minus 11. So I can replace this entire value by one single value, that is 5.56 into 10 power minus 11. Come on guys, try to solve this. Just multiplication guys, should not take so much time. Please answer only in your polls. Guys, answer in your polls please. Poll al answer ಮಾಡಿ chat box al ಬೇಡ. Zoom people, please try to answer in your polls only. Kavya, Karthik, Sai Teja, answer in your polls, don't answer in chat box. Yes, others please try to answer guys. We should not take more than 2 minutes for one question. I have one more question to solve. Yes, cool, thanks. That's it. Yes guys, everyone, so let's check the answer. Okay, so if we try to solve no, if we try to solve, so this is most of you have given me option A as your right answer, correct answer. So yes, option A will be the correct answer guys. So what happens if I try to solve? So try to solve along with me. Lambda is equals to 9 into 5.56 into 2. So 9 to the 18, 18 into 5.56. So I'll get approximately 1000 or 100, right? 9 into 5.56 into 2, I'll get approximately 100 into, now 100 into 10 power 4, 10 power minus 13. 10 power 4 into 10 power minus 13. So if I want to simplify this also, if I want to add this also, 10 power 10 power 4 into 100. How much is it, guys? ಹೇಳ್ಕೊಡಿ ನಂಗೆ ಸ್ವಲ್ಪ. Can I write it as 10 power 7? Yes, correct, Saituja. 10 power 7 into 10 power minus 13. So what is the value? 10 into, okay, 10 power minus 13 into 10 power, yeah, 13 minus 4 estapa. Just simplify that. 13 minus 4 will be, see, yes, 100 into 10 power minus 9. So 9 minus 2 will be 7. So lambda will be 10 power minus 7, right? Coulombs per meter. 100 under 2 alva, 10 power 2 alva. Kavya, check that. 100 means 10 power 2. Okay, so please check. Yes, this is the answer. First option A is the right answer. So guys, second question, I have a similar question to you guys. Try to solve this. ಏನಿದೆ? So uniformly charged conducting sphere of radius, sorry, of diameter. See, instead of radius they have given me diameter. So D is equals to 2 meters. Then what is R? R is 1 meter. And charge density. What is charge density sphere? It should be sigma. Sigma is 80 microcoulomb per meter square. So this is meter square, guys. Find the charge on the sphere. What is Q? What is my Q? Value of Q. So what is sigma, guys? In general, sigma is equals to Q by A, right? Q by A. What is area of sphere? Area of sphere A is equals to. I hope everyone please reply. What is area of sphere? 4 pi r square. Correct. So try to simplify this. Try to substitute all the values. That's it. You'll get the answer. Hope all of you have solved this. Yes, correct. Whoever answered now is correct. Please try to answer, guys. Come on, try to answer. Complete this. Complete this. Okay, guys. Come on, tell me. So sigma was equal to. What is Q? Q is 80. 80 into 10 power minus 6 by A is 4 pi r square. What is 4 pi? Agosh, check your answer. Agosh, yes, check your answer. 4 pi into r square is 12.56. Yes. But but what is given? Okay, shit. So this is very wrong, right? We have to find Q. We have to find Q. What was given? 80 into 10 power minus 6 is equals to Q by 4 pi r square. So this was Q equals to 80 into 10 power minus 6 into 4 pi r square. So what we get? So 80 into 10 power minus 6 into what is 4 pi r? 4 pi r square is 1 square. So 4 pi will be 12.56. What's the answer, guys? Q. We'll get approximately 1000 into 10 power minus 6. Okay, I'll get approximately 1000 10 power minus 6. So if I try to simplify, what should I get? Q as 10 power minus 3 coulomb. So option A will be my answer. So how many of you gave this answer? See. Okay, guys, understood. We derived an expression for electric field and also calculated the expression for electric potential. So yes, done. Oh, guys. So everyone who are new, you could give your feedback in Zoom. So next we will be starting with electric flux. So actually, ideally today we were supposed to start electric flux. So we'll start with electric flux. So what's happening in electric flux? So I'll give you a basic idea, okay? So when we were calculating the electric field for this infinite long charge current carrying conductor, so was it easy for us? Like, was it very easy? Did we solve that in one simple step or two simple steps? Guys, reply. Did we solve in only one or two simple steps, or was it very lengthy? No, right? Was it very lengthy? It was a bit lengthy, right? Yes, it was a bit lengthy. So to eliminate that lengthiness, we have a mathematical tool which was given by George Heinrich Gauss. Okay, sorry, his name is George Friedrich Gauss. I don't know why they used this. Everyone, most of them had this Friedrich Gauss. Okay, this was the guy who gave this theory, George Friedrich Gauss. Uh, yeah. So Friedrich Gauss gave an general expression for the continuous charge distribution cases to find to find the expression. Okay. So Narendra, no, it should be 10 power 3. Please check your answer. So it's approximately 1000 into 10 power minus 6. Narendra, it was 10 power 1000 10 power minus 6. So you get 10 power minus 3 coulombs. Yes, correct. Electric flux is that. Okay. So in electric flux, yeah, we'll learn about this in tomorrow's class. So what happens? Electric flux. So we know in our 11th we had studied this, right? Whenever there is water flow, so my water flows with some velocity. My water flows with some velocity v. When it's in an area of cross section A, my water flows with velocity v. Then the rate of liquid flow or water flow is given by AV cos theta. Correct, guys? Yes. Then my then my rate of flow was given by AV cos theta, where theta was the angle between. What is theta? Theta is the angle between my normal. See, this is my normal, and say suppose if this is my direction of velocity and this is my normal, then this angle is theta. Then the expression for rate of flow of liquid was given by AV is rate of flow of liquid is AV cos theta. Similarly, guys, what happens? Say if I have electric field lines. Say I'll be having electric field lines passing through a surface. So electric field lines, as we have studied earlier, are they visible to us, guys? Is electric field lines visible to us? Is my electric field lines visible to us? No. So we imagine there exists an electric field line. So these electric field lines passing through a surface. Yes, these are imaginary lines, correct, Alvam? So these electric field lines passing through the surface is gives my electric flux. Say number of electric field lines passing through a given surface area will be called as my electric flux. So that is given by phi. So the electric flux through a surface, is directly proportional to number of electric field lines passing through it. So we can make this, yes, correct, Manohar. So we can give this, the electric flux through a surface is directly proportional to the number of electric field lines passing through that surface. So we can say this. So this is the general basic idea of electric flux. No? Why, Bhargav? I don't understand why everyone in YouTube have given this no. Hari Prasad, Ramakrishna Reddy, Bhargav, please answer. What was it about? So we have this, the factors affecting the electric flux. Okay. So we have this, the factors affecting the electric flux. The factors affecting electric flux is given by, so we have several factors which affect the electric flux. So one of the factors is, say, the electric flux passing through the surface depends on the area of the surface. Okay. So if we have more area, passing through the electric field lines. So if I have more area passing through the electric field lines, then I'll be having more flux, right? Flux will be more. Okay, cool, 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 cool. Thank you guys. So if we have more area, more surface area, then we will be having more number of electric field lines passing through the surface. Then the electric flux through this surface will be more. If the surface area is very less, area is less, right? The number of electric field lines passing through this will also be less. Then automatically my flux will also become very less. So what was flux, guys? Flux was nothing but number of electric field lines passing through a given area. Okay. So what is my flux in general? Flux means the number of electric field lines passing through a given area, given surface area is my flux. Now if my area is more, my flux also will be more. If my area is less, my flux also will be less. Second condition, second thing which affects the electric flux is the angle. Angle it makes with the electric field line and that of the surface. So the electric flux depends on the angle theta between electric field lines and the surface area of that surface. Say here in this example, I have a planar surface which makes an angle theta, which is an acute angle. Okay, here my angle is acute angle. What happens? So when it bends more, the number of electric field lines passing through this surface reduces, right? The number of electric field lines passing through this surface reduces. So lesser the angle, less is the flux. My flux reduces. So if my angle increases further, if my angle increases further in this image, in the second image, if my angle increases, what happens with respect to the theta? If my theta increases, my flux or the electric field lines passing through the surface also increases. Electric field lines passing through the surface also increases. Then my flux, net flux also increases. Okay. So this is the second factor in which my electric flux depends on. So third factor, the third factor is the strength of electric field. Say if the number of electric field lines, the number of electric field lines is more. If my strength is more, what happens? If the strength of electric field is more, number of field lines is more or less? Number of field lines ಜಾಸ್ತಿ ಆಗುತ್ತಾ ಕಡಿಮೆ ಆಗುತ್ತಾ? Is it more or less? Obviously more, right? There will be more number of electric field lines. Say if irrespective of my area, the number of field lines will be more. Then if the number of field lines is more, the number of field lines cutting or passing through the area will also become more. Then my flux will become more, right? So if more is the strength, more is the flux. Less is the strength. If electric field is less and area is also less, my flux will be less. If electric field is more and area is more, my flux will be more. Okay, these are the three factors on which my electric flux depends on. So yeah, we'll learn about the expression for electric flux in our next class. Okay. Okay, guys, please give this feedback. This is very important for everyone, guys. Please give this feedback and leave the class. Thank you. Thank you, YouTubers. Bye. So we'll meet again in tomorrow's class. Hope everyone have understood all the concepts which we discussed today. Okay. Cool, guys. Thank you. Thank you for being here. Cool, guys. Then we'll meet again in tomorrow's class.